This last example of an optimization modeling problem is one that comes out of our textbook on page 285. It's number 43, a great business application of the calculus. Here we have a chemical manufacturer selling sulfuric acid in bulk at a price of $100 per unit. If the daily total production cost in dollars for X units is C for cost, equaling 100,000 plus 50X plus 0.0025X squared, and if the daily production capacity is at most 7,000 units, how many units of sulfuric acid must be manufactured and sold to maximize profit? This is a great example of how you see calculus used in the business world. Here we're talking about maximizing profits of a company. Anytime you want to get profit, there is a set way to do that. Profit is always going to be your total revenue, how much money total you take in, minus the cost, your production costs. Now that could include costs for production, as we're told here. It could include costs for maybe advertising, whatever. All right, here we just really have the production costs to deal with. So we need to come up with an equation for the profit that we want to maximize as a revenue minus cost. Revenue is how much total money you take in. In this case, we're told that the company is making $100 per unit. So our revenue in this case is simply 100 times X, $100 for each of the number of units they sell. From that, we need to subtract the cost equation they gave us. Now, the nice thing about this is, notice how we do have a primary equation that we want to maximize in terms of one variable. So this one's pretty simple to proceed from here. I've gone ahead and rewritten what we have for our profit equation. I distributed the negatives, how we were subtracting away the cost, and I went ahead and simplified and combined my similar terms. So we have here a profit equation that we want to maximize of negative 100,000 plus 50x minus 0.0025x squared. We know that we have to take the derivative of that. That simply is going to be 50 minus 0.005. Of course, we have to do the 0.0025 times 2. That's where the 0.005 comes from. Times x, set that equal to 0. Again, very easy to solve. We end up with x is 10,000, and that's our critical number. If there is going to be a maximum for this profit equation, this is the value at which it's going to occur. We've looked at examples in which we've used the first derivative test with the number line analysis. We've seen a couple in which we've done a second derivative test and substituting the critical numbers into the second derivative to determine if we have a relative maximum or a relative minimum. This one I'm going to use the extreme value theorem. Remember that the daily production capacity is at most 7,000 units. So really we do have a domain here. We're assuming they're going to make more than 0 units, right? You can't make a negative number of units. So we really could think of the domain of this function as being 0 up to 7,000, because that's the most apparently that this company can handle making in one day. Since we do have a closed interval for our domain, we can very easily use the extreme value theorem to determine the location of our maximum. We're going to set up a table of values. We have our domain values in there, 0 and 7,000. And we also want to include our critical number of 10,000 that we had. Remember that we substitute into our profit equation. Remember what that was after I simplified it. You easily can do this on your table, on your graphing calculator. If you substitute the original profit equation under Y1 in your calculator, you can go into your table and we'll go ahead and complete our table of values. We have the endpoints of our domain, 0 and 7,000. Now think about what happens when they make no units. I think it makes sense they're not going to have any profits, because they're not making any money, because they're not selling anything. So I think the 0 one makes sense. Obviously, that's not how they're going to maximize their profits, by making nothing. 7,000 units produces a profit of $127,500. So that's possible. Let's check out what happens at 10,000, which was our critical number when we set the derivative equal to 0. That gives 150,000. Definitely looks better, but think about the constraints of this problem. The company's not capable of making 10,000 units. So really they're stuck at 7,000 units until at least they're able to increase their productivity at their plant. So in this case, this is a great example of what happens in real life. They know that they could make more money if they could make and sell 10,000 units, but they're only capable of doing 7,000. So that's really the best they're going to be able to do, is really maximize and sell everything they are capable of making, 7,000 units. In doing so, they have a profit then of $127,500.